Well, hello, everybody. Welcome to our next unit. It's a little very different unit than our last one. Our last one was all kinds of math and reactions and stuff like that. So in this unit, we're actually going to kind of start circling back around to some of the things we did earlier in the year. We're going to take a look, kind of a deep dive into the structure of the atom in this particular one. And then we're going to use that to leapfrog into bonding and how things start to form these chemical reactions and why do they react together and bond together in certain ways. So that's kind of where we're going in this particular unit and kind of between this week and next week. So I'm kind of summarizing a little bit of different things. So hopefully it's not, hopefully I'm not going too fast today. We'll see how this goes. But what we're going to do today is we're going to kind of take a look at an overview. We're going to actually do a little bit of a historical overview because I think it helps for students to understand sort of where we came from to know sort of where we're going. So I'm not going to specifically test you on like who these dead white guys are and how they all contributed their models of the atom. That's not the purpose of this. But understanding sort of how our understanding of the atom has grown can help us sort of build some knowledge so that as we're trying to move into this concept of bonding and how things kind of combine together, there's a context for it. There's a background for it. So hopefully you enjoy this a little bit, at least to get some overview kind of like where we've come from, where we've gone. So I know this picture of an atom that's on here, everybody knows this picture. This is one of the most common iconic images in all of science. Like you ask someone for, to draw a picture of something scientific, and this is one of the first things that they always draw, the Jimmy Neutron model of the atom, right? So it's wrong. That's one of my favorite things about this. Every time I see it, it cracks me up because it's, at the time, which was like 1900, it was great. But it's definitely not right anymore. And it's still this iconic image because it's linked to so many things that we have learned about ourselves and learned about science. So it's sort of humorous to me in terms of seeing this, but I love it. And you're going to kind of learn out a little bit in this one today about sort of where this one came from and sort of how we've moved beyond that. And then we're going to learn a little bit more about how this is related to a really interesting phenomenon called incandescence and light. So it's kind of a weird kind of a process that's going to go on, kind of a combination of things. So here's kind of our group of dead white guys. Now, I'm never going to ask you like who these dead white guys are, but what I do want you to understand is something about how our understanding of what the model is has really built over the last 200 years or so, even a little bit before that. Starting with this guy on the left here, his name is Dalton. In the olden days, we used to think that an atom was literally just a solid object. Like that was the smallest thing that you could get. And that's why they call that the billiard ball model. And then as we built upon that, we started to add different things to it. So like in Thomson's model, he started to learn some things about electrons. And he used to call it the plum pudding model because he was British. Americans, we usually call it either like the blueberry muffin model or the chocolate chip cookie model. But that idea that he was one of the first guys that actually invented the concept of electrons. And if you've ever seen the really old big TVs, the CRT TVs, that was based on Thomson's original work, that understanding that electrons are a thing, that they exist apart from atoms, we can shoot them through different materials. It's part of what electricity is based on, for Pete's sakes. It's kind of a cool idea that built on that model. And then Rutherford, there's our Jimmy Neutron model. See, 1910, that thing has been around that long, over 100 years ago at this point, that was the picture of the model. His advancements were that not only did you have electrons, but they were kind of buzzing around the outside, but then also he had the idea of a nucleus. And I know you know these terms, you had middle school science. So he had definitely a big, a growth in that understanding of what the structure of an atom was. And then right along the same time, this guy Rutherford and his buddy Bohr worked basically at the same time, almost in the same lab. See, the times are really close together. Bohr came along and said, you know what? I don't think that atoms, the electrons are moving around in these kind of like weird particles like this crossing over each other. I'm thinking that they're in this thing called energy levels. And this is that solar system model that, again, I know that you've seen. So again, just a kind of a construction, a build upon that. And then now today, Schrödinger and a bunch of other smart guys like Einstein and some other dudes that were along the same line started to kind of redevelop this idea. And it's gotten even messier. So when you start people are starting to talk about quantum tunneling and the quantum understanding, they start throwing that word in there. This is because we now know even more about how electrons work, and they're even messier than we ever possibly imagined in the ways that they behave. And so we're going to I kind of want you to live somewhere between these two. We're still going to use Bohr's model quite a bit because it's easy to draw and it's easy to understand. But I also need you to know that electrons aren't little things that are flying around little orbits like planets are, that they're definitely fuzzing around in some different ways. And so that's kind of my goal today, is to kind of get you to see a little bit of that finesse in between there, to make a little bit of that transition in the newer model. So going to kind of back up to Rutherford versus Bohr and how they were kind of coming at this idea of what was happening in atoms. So these guys were actually studying a really simple phenomenon called incandescence. You know what incandescence is? You just didn't know the name of this word, or what this word means. This used to be called an incandescent light bulb, or that's a regular light bulb, as people my age would call it. I know you guys now are used to fluorescent light bulbs and LED light bulbs, but it used to be you'd take a piece of wire, you run a bunch of electricity through, get it real hot, and it would glow. And you guys know that when you have real hot metal that it glows. And so these guys were sort of studying some of the phenomena that happened with incandescence. Why is it that hot atoms or hot material gives off light? This is the connection that we're trying to make here. How is it that matter can emit light? We know that light is a form of energy and not matter. So how are those guys related to each other? And how does that tell us anything about the structure of an atom? They went a little bit further. So rather than just heating up sort of generic things, they would heat up samples of single elements. And there's kind of two different ways that you can do this. If we were in lab at school, this is one of my favorite labs to do. We would actually do this thing called the flame test. We would take little samples of these different elements and we'd burn them, and they give off different colors of light. So not only do they give off light, but they give very distinctive colors of light. For certain types of materials that are in gas form, we can put them in a tube called an emission tube. These are literally glass tubes, almost look like light bulbs in a sense. And you run a bunch of electricity through them and they will glow. And you can see these all glow different colors too. Like xenon is, you've seen xenon headlights maybe in cars. They have that kind of weird, eerie, kind of bluish kind of color to them. And I know you've seen neon lights before, like down at State Line. Those are those red glow in the dark kind of lights, like an open sign, not the LED version of it, the older school ones where it's like the bent tubing. Those are neon lights. And again, that's a sample of neon gas that's in there with electricity flowing through it. And these guys particularly studied hydrogen and helium because those are the simplest atoms, simplest elements. They knew that hydrogen and helium were elements number 1 and 2, the absolute simplest, smallest atoms that were out there. So they thought, well, you know what? Maybe if we study these two simple atoms, that'll give us some perspective into what's actually happening inside these atoms, and we can learn more about how they're put together. So in order to kind of make the connection between these two, you need to know some things about kind of what light is, because we know we've got matter, and they're trying to figure out what matter is and the structure of matter, what's going on inside that atom, right? And we know that it gives off energy. So we need to know something about that energy as well. So we know that they give off light and particular colors of light. So one of the things that you should be aware of, take some notes, right, is that light is what we would call electromagnetic radiation. It's a wave. And I know you've seen sine waves before, but we can talk about sine waves in terms of their wavelength and their frequency is one way that we characterize these. So you can see a short wavelength, they're real close together. Those peaks happen really often, so we'd say that's high frequency, versus a long wavelength. There's a lot of space in between each one, and they're kind of, they happen less often. They happen at the same speed. They still travel across, it's still light. It still travels at the same rate. But in terms of the number of crests that happen in a second, they're a little bit different. And with light, we experience wavelengths and frequencies as colors. And this is kind of a cool thing that when you change the wavelength of the energy, you actually change what it looks like. So on the one end, you have this long wavelength light that's red light. And as you get progressively shorter, our eyes start to perceive it as being blue and then into violet light. And violet light is the shortest wavelength that we can see. And this is actually part of a much bigger range of light that's out there called the electromagnetic spectrum. So in the middle here, you can kind of see the visible light section. You've got the long wavelength side over here, which is red light, and the short wavelength side over here, which is violet light. And you can see that it goes even beyond that. The colored light that we can see, sorry, I need my pen, is just a really tiny little slice of the entire range of the electromagnetic spectrum. This little tiny bit right here, that's the only part of electromagnetic light that we can see. The even longer wavelength lights are things like we would call infrared or heat light, if you want to call it that. Microwaves, not the appliance, but what the appliances make. And then radio waves, and cell phones are kind of down in here in this microwave range. Cell phone rays are down here. These are what we would call low energy, long wavelength forms of light. And then on this violet end of the spectrum, we get not just violet, but ultraviolet, right? Extraviolet. These are even shorter wavelengths than violet light. And so you guys know that these things, and here we even use the word rays on these, like ultraviolet, X-rays, gamma radiation. These are the high energy forms of light. And again, these are the ones that are more dangerous for us. You guys know that ultraviolet light can cause sunburns, if nothing else, right? X-rays, they can penetrate skin and actually, you can use them to take pictures of bones because it can travel right through your skin. But you know that those are dangerous. You don't have a lot of X-rays. And gamma gamma rays is actually what causes radiation poisoning. So like Hiroshima and Nagasaki and the horrible fallout that happens from radioactive materials is in that gamma radiation. No, Hulk would not have survived that, but and then that was gamma radiation. But anyway, so these are the high energy forms. So we've got this idea that there's different colors of light, and that's related to wavelength and frequency. But yet the purple side is that high energy side, and that the red side is the low energy side. So there's something between color and wavelength, but also color and energy. And these are the two things that go along with this, because we know that when they ran energy through different types of atoms, they gave off different colors. So there's something about the energy that goes along with this. So again, tying it back to this idea here, this is a hydrogen tube, and this is what hydrogen would look like if you put it in one of these glow tubes and kind of set it off. They use a real particular piece of information to kind of analyze the light that was coming out from hydrogen. They wanted to look at the colors and the energies that was coming from this phenomenon. So they use something called the diffraction grating. These are rainbow glasses. You can use these all the time. They sell these at like raves and stuff like that. You can go get them online. But again, it allows you to kind of spread it out, and you can see the spectrum. Like crystals will do this as well. Well, they'll spread it out into that rainbow. When you've got white light, this kind of material will allow you to see the colors that are within the white light, even though our eyes kind of blend it together. So when they looked at this hydrogen and the energies of light that it was giving off, they found some really interesting phenomena occurred. And you can kind of see it here in this one. So what this is a picture of here is here's your hydrogen, but over here you can see what that hydrogen light looks like when it's passed through that diffraction grating. And you can see that there's some of these different colors, like there's some bright spots and dark spots. So they knew that there was some higher energy light and some lower energy light that was being given off within all the light. It's just different. And not only that, but every type of element gave its own unique spectrum off. Now, this was really blowing their minds back at this time. This didn't make any sense in the Jimmy Neutron understanding of how an atom worked. So they knew that hydrogen gave off real particular colors, and they could tie these particular colors to particular energies. And so Bohr came along. He was the guy that did the solar system model back on. He's the guy that looked at this stuff and said, you know what, Rutherford, I think that your Jimmy Neutron model is cute, but it doesn't really work because there's something going on here with different electrons doing different amounts of energy based on these colors. And so his grand idea that when he came along with this is that every element must be giving off its own unique signature. And we can see them. This is what these unique little fingerprints of color look like. It's kind of cool, actually, that everyone gives off their own color. So there must be something unique going on with the electrons inside each atom. So back to the atomic structure. We're almost done here, I promise. So with this, the way that he interpreted it, and this is that big idea that I kind of want you to get, going from color to energy levels. I mean, that's a huge leap of energy. This guy was brilliant, man, that he came up with this idea. His idea was that electrons weren't just bouncing around completely randomly like Rutherford's, where they're just sort of going on all these hectic circles, that they were highly organized in these different energy levels. And he pictured them like being orbits. So that's where he had that drawing where he had the nucleus in the middle and some electrons that were in the first energy level and electrons in the second energy level and electrons in the third energy level. And what he said was that the colors that were being given off were from when these electrons were starting in one spot, jumping up someplace, and then falling back down. And that absorbing and releasing energy is actually what caused the colors. And if it was a small jump like this one, where it's literally just going one single energy level difference, that it would give off a relatively low energy color of light, which would be red. And if it was going up 2 steps, up 2 energy levels and falling back down 2 energy levels, then it would give off a little bit higher energy color of light, like this blue-green color. And then if it was going up 3 steps and falling down 3 steps, that must have been an even bigger energy jump, and that would be giving off this blue to almost violet colored light. So this is how he made these connections between all of these crazy stripes of color that we see, is that all of these different colors of light is due to different electrons that are jumping around from energy levels. You've got smaller jumps down here on the red end, and you've got bigger jumps up here on the blue and violet end. But these are all of these electrons that are bouncing around. We happen to be able to see a few of them that give off some colors that we can see. So again, his big idea is the concept of energy levels, and we still use this today. The concept of energy levels is still there, and we're going to use this in our next bit of drawing that we've got. That we still have these things. We now call them energy shells or energy levels, but there are these lower lower energy levels towards the middle, and then the energy levels get bigger, bigger, and bigger. I know you've drawn these kind of models back in middle school. We call them Bohr's model or Bohr models as we draw these, so that we've got spaces for electrons to hang out, that those electrons can temporarily jump up and then fall back down and release some energy. And this one could jump up and fall back down and release some energy as it does that. And that's the reason behind the color that we see. So again, this is just sort of a kind of a big picture kind of thinking about some of the crazy things that's happening with our understanding of how color and light works, and then how our sort of our development of our model of the atom has happened. And even today now, the people that are studying atoms and how they work, electrons don't even function like this. They go even crazier than this, but we're not going to get into it here. If you take Chem 2, we'll go into more about what that kind of works. So there you go, kind of an overview of sort of our development of the model of the atom, the importance of electrons and the absorbing and releasing of energy in this, and then how we can use the Bohr model, even though it's not correct, but how we can use the Bohr model, that idea of energy levels, to give us a picture of where electrons sort of are hanging out within a particular atom. So Bohr model, we're going to use this one in our next video as well. So make sure you have some idea how that works. And I'll see you in part 2. Thanks, guys. Bye.